Hello everyone, my name is Zhenghua Lü. I am from Vimeo. I am the software engineer of Greenplum. Today I'm going to share our paper. The title is Greenplum, a hybrid database for transactional and analytical workloads. The agenda of today's lecture is shown in this slide. First, we will show the different evolution of data processing workflow, and then we will have a brief introduction to Greenplum's MPP architecture. Next, we will dive into the H-tab optimization in Greenplum. Finally, we will show the benchmark result with our optimization. Now let's come to the first section of this talk, the evolution of data processing workflow. Here we use a picture to show a traditional enterprise data processing workflow. You can see from the picture, this whole system is very, very complex with different kinds of tools and platforms. Application generate SQL using some ORM and send them to traditional transactional system. Then transactional system either use streaming processing tools or batch processing tools to save the data into a data warehouse. Then a BI report system connected to data warehouse to generate the BI reports. So the reports are often based on non-real-time data. So a question is, can we put all the complex modules into a system? That is, data processing workflow for H-tab database workflow only includes one platform, and so that BI reports is real-time and with full ACID support. There are different evolution paths from H-tab databases. One path is from OLTP to H-tab. Some typical cases are Oracle and Aurora. Another path is from NewSQL to H-tab. Typical cases are Google's S1 and TiDB. Greenplum shows another pathway to evolve into an H-tab database. Greenplum add OLTP capability to a traditional LAP database. Now let's come to next section. In this section, we will have a brief introduction to Greenplum. Greenplum is massively parallel Postgres for analyticals. It can handle petabyte scale of data. You can deploy Greenplum everywhere. And Greenplum not only supports a BI system, but also it contains a module called MATLAB that can support the computation of artificial intelligence. Greenplum is open source, and the license is Apache license. This slide shows Greenplum's MPP architecture. It consists of different segments. Among all the segments, one is called coordinate. It directly connects to the client, generate the distributed plan and manage the distributed transaction, and dispatch the plan to all the segments. Each of these single segment is an enhanced Postgres instance. It is important to understand the distributed plan and the distributed executor of Greenplum. Not only it is important of the It is very important to understand the distributed plan and distributed executor in Greenplum. This is a key step to understand the following optimization on each tab. Table in a MPP database, the data is saved in every segment. Each segment locally only contains a small portion of the data. When you are doing a join or HG in globally, at some point, data has to be moved to some place so that the join condition cannot be matched across segment. Greenplum uses motion plan node to abstract this kind of data movement. Motion cut the plan into slices. Each slice is executed by a group of distributed process. When the group of process are called GON. In this picture, we have an example of two tables joined, and the table are distributed in different policy. The middle shows the plan in different colors means different slices. And the right picture is the running instance of the distributed plan. The yellow slice scan the classes table and then send it via motion to the blue slice. The blue slice scans the students table and receive from the motion, then do a hash join. Then it sends data to coordinate via gather motion. Another important feature that enhances Greenplum's H-tab capability is the hybrid storage and optimizer. Greenplum supports different storage types for different applications. Heap table is suitable for frequently update or delete operation, typically the OLTP workloads. Append-only storage, either row or column-oriented, can support data compression to save a lot of space. Thus, they are useful for OLAP workloads. User can also choose external table such as S3 or HDFS to save the less accessed data. Combined with partition table, user can design a flexible storage policy for each leaf partition. The following is a practical example. The table cells are partitioned by time. For those less accessed data, we archived them to save them in external table of S3 or HDFS. For those data that does not need to update or delete frequently, we choose append-only column-oriented storage type so that we can compress the data and save a lot of space. For those data that need to update or delete very frequently, we choose heap. There are two optimizers in Greenplum. Orca is designed for handle complex OLAP queries. It has many advanced features. For example, for the optimization of CTE query or complex sublink pull-up. Another planner is based on Postgres planner. They are suitable for simple OLTP queries because the planning time are small. To be noted, the performance of planner in Greenplum 7 is much, much better. Now let's come to the core part of this talk, the H-tab optimization in Greenplum. Let's first talk about the global deadlock detect algorithm. Before we dive into the algorithm, we first introduce the concept of global deadlock in Greenplum. Logs are widely used in database to do concurrency control. In a single segment database like Postgres, insert, delete, and update these kinds of DMLs are allowed to run concurrently. Here, by concurrently, we mean they can run parallel if they are not touched the same tuple. But in a distributed database like Greenplum, things are more complex. If you allow these DMLs to run concurrently, global deadlock may happen. In the right picture, there is an example of global deadlock in Greenplum if we allow these kind of DML to run concurrently. The ID in the box is the execution order. First, the transaction update the table T1 of the tuple with the column C1 equal 2. Then transaction B update the same table T1, but the different tuple with column 1 C1 equal 1. Then transaction B continue to update the tuple which just updated by transaction A, and this tuple is on segment 0. So transaction B has to wait for transaction A on segment 0. This is a transaction log wait because they are both writing the same tuple. At this time, transaction A is not blocked, so it continues to execute an update statement. Transaction A updates the tuple that just updated by transaction B in step 2. And that tuple was on segment 1. Then transaction A has to wait for transaction B on segment 1. So on segment 0, B is wait for 1 wait for A. On segment 1, A is wait for B. Globally, transaction A and transaction B are wait for each other. So this is a global deadlock. But to be noted, on each local segment, there is only one wait for relation. So there is no deadlock locally. Postgres' local deadlock detector cannot handle global deadlock in Greenplum. Here is a more complicated example of global deadlock in Greenplum if we allow DMLs to run concurrently. This case involves the coordinator in a global deadlock. We are not going to dive into the details here. To understand the global deadlock detect algorithm, there are two important concepts need to keep in mind. First, the algorithm is based on greedy rule. By greedy, we mean that if a transaction is not blocked by anything, we can assume that it will be over in next step. Second, there are two kinds of wait for edge in the wait for graph, a solid edge and a dotted edge. A solid edge means the edge can only be gone after the resource holding transaction is over, either abort or committed. The dotted edge means that the wait for relation does not depend on the lifetime of the transaction. Now let's go through the algorithm. The algorithm begins after we collect all the wait for graphs from each segment. Then we have a global wait for graph on the daemon on the coordinate. It is a while loop. And at the first stage of the while loop, we keep removing the edges that there is no outgoing wait for edges. These are transactions that are not blocked by anything. By greedy rule, we assume that they will be commit or abort right now. And let's remove all the edges at this point. Next, we go through each local graph and find those without any outgoing edges and find all the edges that in this vertex. For those dotted edges in the local graph, they can be removed because by dotted edges, we know they are not their lifetime does not depend on the transaction's lifetime. By the greedy rule, we can assume the resource held by the endpoint of the edge will be released right now. We keep removing edges. Once we find that there's no edges can be removed from the global wait for graph. Let's see if there are any vertex left. If so, there is a global deadlock. Before the final decision, we have to check to make sure that all the vertices representing the transaction still exist in the system. Now let's come to a detailed practical example to show the global deadlock detect algorithm. On the left part of this slide is 3 transactions execution steps to form a scenario. On the right part of the slide is the algorithm's execution steps. We can see from the picture the data distribution and the global waterfall graph. So beginning from step A, we have a global waterfall graph. On segment 0, there is only one weight for relation. B, transaction B is weight for transaction A, and the weight is a solid edge weight. On segment 1, there are 2 weight edges. Transaction A is waiting for transaction B. This is a dotted edge weight. And transaction B is waiting for transaction C. This is a solid weight edge. And then let's running the GDD algorithm. First, transaction C is not blocked by anything. So we can safely remove transaction C by the greedy rule. And then we get the step 2. In step 2, there is no vertex has a global 0 degree. So let's go through each segment's local waterfall graph. On segment 0, there is no dotted edges. On segment 1, there is only one dotted weight for graph. So we can remove these edges. Then we get to step C. In step C, there is only one weight for relation left. We can safely remove it by the greedy rule. Finally, there is no edge in the graph, so there is no deadlock in this scenario. One thing important to be mentioned here, if transaction C is abort, then transaction A and transaction B will form a global deadlock. So someone may be asked, so this is really a global deadlock issue, but your GDD algorithm does not detect it. Really? No. This is the correctness of a GDD algorithm. We can handle different types of isolation level. If the isolation level is read repeatable, then if transaction C is commit, then transaction B will abort. Thus, there is only one transaction left in the system, so no deadlock. Next, let's talk about distributed transaction management optimization in Greenplum. Two-phase commit is used to ensure the consistency among all the segments, but sometimes if only one single segment generates X log, we can use one-phase commit to save network ping pongs. This part is not theory novel invention. It's just some engineer optimization. Also, resource isolation is very important in a HTAP system. Analytical workloads have heavy impact on transactional workloads through output. In Greenplum, we introduce resource group to do resource isolation. User can put different workloads in different group, and they can do CPU isolation and memory isolation. Finally, let's come to the benchmark result. In the left slide, picture of this slide, we show the huge performance gain of OLTP performance of GPDB6. And on the right picture, we show the scalability is better than Postgres. And this slide shows the HTAP performance. We can see the performance is much better compared to GPDB5, the previous version. Greenplum allow DBA to tune each resource group's parameter to achieve different performance for their workload. Thank you for your time.